Hello everyone, I'm Norman Wahlberger and welcome to the Algebraic Calculus. In today's video we're going to talk about quadrants, perpendicularity and pedal curves, moving towards a more accurate understanding of the motion of an orbital planet around the Sun. We're going to correct Kepler's wrong views about the relationship between velocity and position. Okay, so we're going to introduce some important ingredients here that will be important for us in the algebraic calculus because although we're sort of starting off in an affine setting, for a lot of applications we want to introduce metrical structure. So we want to make that metrical structure fit harmoniously with the affine setting that we've so far established. And we want to maintain the algebraic purity of the direction that we're going. So to do that, we're going to have to depart from traditional thinking, and we're going to have to introduce aspects of rational trigonometry, which I hope you all know about. If not, please learn something about it. But I'll teach you a little bit about it this time anyway. So affine geometry is basically a geometry, a planar geometry, say, based on the notion of parallelism. And with parallelism, we can do a lot of things. We can talk about vectors. We can talk about signed areas. We can talk about conics. We can talk even about tangents to, say, a conic or a more general curve at a point. So there's lots of things that we can do, but it is the case that we don't really have a sense of measurement aside from being able to compare segments in an equal direction and being able to compare areas. Now, when we go to metrical geometry, which is usually thought of as an extension of Euclidean geometry, that's the sort of standard metrical geometry, we want to introduce more structure. So we're taking affine geometry and imposing metrical structure that allows us to talk about things that we couldn't talk about in this more general setting, this more specific setting. And the kinds of things that we can talk about over here are, first of all, quadrants. So crucially, not distance. You might think that distance is an important thing. You might think that angles are an important thing, but they're not. Okay? Distances and angles really don't play a proper role in Euclidean geometry the way Euclid thought about it, and also not the way we're thinking about it. But quadrants is the square of the distance, and it's a purely algebraic quantity, and that does fit in harmoniously with the Cartesian framework. Very important concept. Once we have quadrants under our belt, we can talk about circles, which are now special types of conics that come into focus in this metrical situation. And we can talk crucially about perpendicularity. That's actually quite connected with the idea of a circle, because if you have a radius of a circle and a tangent at that point, then necessarily the radius and the tangent are perpendicular. So the circle kind of embodies perpendicularity. Okay, what about physics? Well, physics kind of straddles these two things. So there's quite a lot of aspects of physics which are independent of a metrical structure. For example, momentum, forces, vectors, velocities. Those kind of things are often independent of a metrical structure. But some things, like Newton's law of gravitation, definitely have a metrical aspect. So if we're understanding physics, we have to augment our affine geometrical point of view with some metrical geometry as well. And then when we go to relativistic geometry later on, well, then the nature of the metric changes, but still the basic principles that we're establishing over here, if we do it right, will still harmoniously extend. These days, by far the easiest and logically cleanest way of talking about metrical issues in geometry is via linear algebra. This is a relatively modern development. It's a 20th century development largely, and it provides a language and very standard important tools that are just ideally suited to introduce metrical ideas. But maybe this understanding is still not widely accepted in the geometrical community. So there's a difference of opinions there, but our point of view is firmly in the direction that linear algebra is sort of the key framework to think about metrical structure. So that means that we're especially interested in thinking about things from a vector point of view and establishing the metrical structure at the level of vectors. And the way we do it is through a dot product. Fancy term is symmetric bilinear form. And here is the dot product that we're going to be using, at least for the first part of this course, the standard Euclidean dot product, given by the formula AB dot CD equals AC plus BD. So given two vectors, the dot product gives us a number. And with this dot product at our disposal, we can very quickly define important auxiliary quantities, primarily perpendicularity first. So two vectors u and v are perpendicular precisely when their dot product is 0. Dot product equals 0 means that the vectors are perpendicular. So for example, the vector 1, 3 is perpendicular to the vector 6, minus 2. In this picture, 1, 3 and 6 minus 2 are perpendicular. When we introduce a dot product, we want to be more rigid about the way we're presenting our affine coordinate plane, our grid plane. We want it to look more like an actual piece of graph paper with the axes looking perpendicular to us and with these segments equally spaced in the x direction having the same separations as the y ones in the usual sense of same. Like measure that one, they're the same. So then the vector 1, 3, the vector 6, minus 2, geometrically you can see that they're perpendicular, and algebraically they're perpendicular because 1 times 6 plus 3 times minus 2 is 0. And then the other crucially important quantity that we can introduce just via the dot product is the quadrants. The quadrants of a vector. The vector v has coordinates a, b, then the quadrants of v is v dot v. Just the dot product of the vector with itself. And that'll just be a squared plus b squared, the quadrants of a vector. So hopefully you've learned about the dot product in a linear algebra course. If not, you can have a look at my Wild and Algebra series. But here are some of the familiar, I hope, fundamental properties of the dot product. First of all, it's symmetric. If you interchange the order of the vectors, the number doesn't change. And here are the linear properties, or more precisely, the bilinear properties of the dot product. So if you fix one of the vectors and look at the linearity in the second variable, then it's linear. And in terms of adding and also in terms of multiplying by a scalar. And it's the same in both components. In terms of perpendicularity, well, if u is perpendicular to v, then v is perpendicular to u. That's an immediate consequence of the symmetry of the bilinear form. And this is a little bit more subtle, that if u is perpendicular to v and v is perpendicular to w, then u is actually parallel to w. Of course, parallelism can be described by the cross product being 0. And properties of the quadrants, well, let's say the simple ones, that it's a quadratic expression, so that if you multiply a vector by a scalar lambda, the quadrants changes by a factor of lambda squared. And in the Euclidean case, we also get this additional important property that the quadrants of a vector is 0 precisely when the vector is 0. Because a squared plus b squared equals 0, that can only happen when a and b are both 0. So those are some elementary properties of the dot product and how they feed into perpendicularity and quadrants. So once you introduce metrical structure, there is one very important theorem, sort of the most important theorem in mathematics, which is Pythagoras' theorem, which was known to the Babylonians, called the diagonal rule. But here's a vector form for it, which is very convenient. So a triangle ABC, and we'll describe it in terms of the vectors forming the sides. So that's the vector u, that's the vector v. Then this vector here from b to c will be the difference between the two vectors, so it'll be v minus u. So these three things. And Pythagoras' theorem says that these two vectors here are perpendicular precisely when a certain condition is satisfied between the quadrances of the three sides, or the three vectors. Precisely when the quadrants of u plus the quadrants of v equals the quadrants of this third vector, v minus u. There's no distances involved, crucially, no distances involved. It's not the sum of squares of distances equals another square of distance. No, okay? It's about quadrances. which is just a modern reformulation of the way Euclid thought about it in terms of areas of squares. That's geometrical interpretation. The proof is quite elegant. It's perhaps the simplest proof that this expression here, QU plus QV equals Q of V minus U, that's equivalent to, just put in the definitions, U dot U, that's what that is, plus V dot V, that's what that is, equals V minus U dot V minus U, that's what that is. And then if we examine this and use the bilinear properties to expand this right-hand side, there will be a V dot V, there will be a minus V dot U, there will be a minus U dot V, and there will be a plus U dot U. The V dot V and the U dot U will cancel with the same terms on the other side. And the minus U dot V minus V dot U will combine because of the symmetry to give minus 2 times U dot V. And then since we can divide by minus 2, that's equivalent to U dot V equals 0. So the perpendicularity, which is expressed this way, is equivalent to this algebraic relation between the three quadrances. And it's just about the simplest possible relation you can imagine. This quadrant plus this quadrant equals that quadrant. So this is a very elegant and actually powerful form of Pythagoras' theorem. So this is in some ways a far better proof, really, conceptually, than most of the dozens of proofs that are out there. Because once you understand this proof, first of all, you appreciate how simple it is, and you also appreciate that it's very general. Okay, you have a symmetric bilinear form, different symmetric bilinear form, a relativistic form. You're working over a different field. Doesn't matter, just algebraic, so it works. It'll also be important for us to have an understanding of the fundamental connection between quadrances and areas, or signed areas, because signed areas are very important for us. And this is contained in a result I'm going to call Archimedes' theorem, which is more or less a rational version of Heron's formula. It's like you take Heron's formula and you soup it up to be more general and more powerful and more algebraic and more correct, and you get this. But because Archimedes almost surely understood Heron's formula before Heron did, we're going to call it Archimedes' theorem. And I'm expressing it in terms of quadrances between points now. So if you have 2 points, A and B, then the quadrants between them is just the quadrants of the vector AB. That gives us the quadrants between 2 points. Okay, so now if we have 3 points, A1, A2, A3, and we have 3 quadrances, and we like to denote them this way. So Q1 will be the quadrants between A2 and A3. Q2 is the quadrants between A1 and A3. And Q3 is the quadrants between A1 and A2. So we have this triangle, these 3 quadrances, and then the statement is that if you take the signed area, and you can go in either way, it doesn't matter because we're going to square it. So the signed area squared times 16 is an expression that can be completely calculated just via these 3 quadrances. And there's 2 important alternate forms of this. One is symmetric, the other one's not so symmetric, but maybe a little bit simpler to use. So the non-symmetric form is 4q1 q2 minus q1 plus q2 minus q3 squared. That's actually just one of 3 possible similar forms. But if you expand this all out, you see that you can rearrange it into this symmetric form, which is also very attractive. Q1 plus Q2 plus Q3 squared minus 2 times Q1 squared plus Q2 squared plus Q3 squared. So this is the difference of what I call the triple quad formula. So in particular, if the 3 points are collinear, then the triangle has 0 signed area, the left-hand side is 0. In that case, this quantity is 0, which isn't saying that this quantity is equal to this quantity. So for example, if A1 is 0, 0, A2 is 5, 1, A3 is 3, 2, then you can check that the 3 quadrances are 5, 13, and 26 by taking half of a cross product. The cross product of the vector 5, 1 and 3, 2 will be 10 minus 3. That's 7 divided by 2. That's the signed area. And in terms of the expression here, if we use this one here, 4 times 5 times 13 minus 5 plus 13 minus 26 all squared. This is 260. This is minus 8 all squared, that's 64. There's a minus sign, and so you get 196, and that is indeed 16 times 49 over 4. So in other words, 4 times 49. So it does work. So before we get to the topic of the Kepler motion, I want to introduce the idea of a pedal curve. This is a pleasant thing that geometers think about. So if C is a curve and P is a point, then the locus of x, which is the foot of the altitude from P to a tangent line of C, is called a pedal curve of C. So what does that mean? So here's a curve C, it's my drawing of an ellipse, and here's a point P, which happens to be close to the center of it. So to get the pedal curve for this curve and this point, what we do is we consider variable tangents to the curve. Okay? So if we take one of those tangents, say this one here, then we consider the foot of the altitude from P to this tangent. And crucially, that involves the notion of perpendicularity. So that's a notion that only makes sense in our Euclidean story after we've introduced metrical structure. So we get that point right there. That's a point on the pedal curve. Then we choose a different tangent, say that one there, we would get that point. If we choose this as the tangent, then the pedal point would be that one. If we choose this tangent, the pedal point would be that one. So then the locus of this foot of the altitude will draw out or trace out this curve that I'm drawing here in red. Okay? So it sort of hugs the ellipse, but it sort of wobbles away from it and then comes back in. Okay? That's the pedal curve of the curve with respect to the point. So if we change this point, kept the curve fixed, well, then the pedal curve is going to change. So a given curve has actually lots of pedal curves associated with it. Okay, it's a kind of an interesting, curious way of constructing new curves from old ones. It's the kind of thing that geometers like to investigate. But it's actually quite important for the story of the orbital motion of planets around the sun, as Newton ultimately ended up realizing. Now there's one more additional fact from geometry, a very fundamental one, that we have to transfer into this rational setting to apply to the Kepler story. And that's what we might call Euclid's theorem, which gives an alternate form for the area of a triangle in terms of a base and a height. So Euclid's theorem, usually in primary school and so on, is taught in terms of lengths. Okay? But when we go to this Cartesian setting, exact algebraic formulation of things, we cannot import distances in an exact fashion. So we have to think a little bit broadly. And the way we do that is to replace the distances, of course, with the quadrances. That tends to mean that we want to square traditional equations to bring them into this rational trigonometric framework. Okay, and here's the theorem that here's a triangle ABC. The quadrants from A to B, we'll call that Q. And this is the way I like to denote a quadrant, so a little rectangle along the side. So alerting you to that that's a quadrant, not a distance or length. And we also have an altitude quadrant from the other vertex perpendicularly down to, say, a point P. We'll think of that quadrant as being H. Okay, so we have these two ingredients now, Q and H. Then the signed area of the triangle squared is H times Q over 4. So the traditional way we learn Euclid's theorem is that the area is equal to 1/2 base times height. When you square that, you get the square of the signed area equals the product of the quadrants is now divided by 4. And note that the signed area is here squared, which means that we don't have to fuss around about which orientation we're taking. We just had signed area, then we would have to worry about which orientation it is because one orientation is the negative of the other. But with these formulas involving some metrical geometry, algebraic ones, typically what happens is that you see a formula for the square of a signed area so that the orientation ends up not mattering. It's independent of the orientation. That's exactly what we have here. And notice that no use of angles is allowed here. There's no angles here in terms of, this is sine of that times some length or something. None of that. It's all got to be algebraic. We have to be able to compute everything down to the last drop, and circle it, and there's the answer. So our geometry here is not the usual kind of, wave your hands, use a decimal approximation, look up an approximate trig value kind of thing that we do in, a lot in the modern mathematical community. No, we're interested in geometry which is completely exactly precise, because our calculus is going to be completely exactly precise. That's what we're aiming for. So the ingredients have to be also logically coherent. So now we're in a position to explain the true relation between the velocity and the position on Kepler's orbits. So we're going to replace Kepler's false thinking that the velocity, the speed actually, the absolute value of the velocity was proportional to 1 over the length from the sun to the planet, the distance. It's not 1 over the distance, it's actually something else. And so to understand that, let's suppose that we have the sun here, and we have the orbit of a planet or a comet in some conic section, and here are two nearby points, positions, pi and pi plus 1. And we'll suppose this is relatively small, and there's a separation there of delta s. It's a length. So the physicists are using lengths and distances. That's fine. That's understandable. Okay, so there's a length of delta s there. And here's our triangle. And Kepler has taught us that the rate of change of that triangle's area is proportional to the time. Okay, so what that means? That means that the change in the area from here to here is k times the change in time. That's Kepler's second law. Okay, now by Euclid's theorem, in this ordinary sense with distances and so on, what's happening? The triangle's area can be expressed in terms of base times height. Okay, so what's the base and what's the height here? Well, we're going to look at it from the point of view of this being the base up here. So this is the base. Okay, so this is like the ground here. You have to kind of think about rotating your view. And this is the third vertex. And so Euclid's theorem says that we have to take this length times the height, which in this case is this height between this sun and the tangent. Okay. So that's actually exactly like a pedal curve kind of situation. It's exactly the same thing you do if you were creating the pedal curve of the conic's trajectory with respect to the sun. You would look at this tangent and you would project this point vertically onto that tangent. So what we're doing here is we're taking that quantity and calling it p. That's the distance p. So what are we learning from Euclid? Euclid tells us that the area of the triangle is 1/2 base times height. So we don't have to use quadrants in this case because this is a physics thing where there are distances and such involved. Okay, so the base is delta s. The height is this quantity p that we've just introduced. We have to divide that by 2. Okay, so now we have two expressions for the area of this triangle in terms of this constant k, which is some constant that depends on masses and such. Okay, so if we take this thing here and we take this and want to compare them, we want to get rid of the triangle's area. So we could take this formula and divide it by this formula. Okay, so there'd be a delta s over a delta t k2, p equals 1. Okay, so if we divide this formula by this formula, then you'd get delta s over delta t equals, on the other side you'd get 2k over p. Okay, so that's a consequence of dividing this formula by that formula. And if we look at this, what is this saying? The delta s over delta t, that's the change in position over the change in time, that is the velocity. Okay, if the thing is small, it's the sort of instantaneous velocity. And on the right-hand side, we have 2k. K is some constant, which is fixed. And crucially, p in the denominator. P is the perpendicular distance from the sun to the tangent to the point that we're considering. So the velocity is proportional to 1 over the pedal distance to the tangent. And now we can see why Kepler was a little bit confused, because when the particle is at its nearest point and also its furthest point, let's say happens to be the nearest point, then the tangent is like this, then the vertical distance to the tangent will be exactly the same as the distance. Okay? So exactly in these two extreme points, this quantity is equal to the distance, and so it's not surprising that Kepler made the mistake of thinking that V is proportional to 1 over R was the general formula. But it's not V proportional to 1 over R, it's V proportional to 1 over P. So we can see that just a little bit of geometry clarifies what's going on there, and this was understood by Newton and forms part of the story that eventually we want to lay out in some detail of how Newton applied calculus to explaining Kepler's laws, getting these conic section orbits. So there's much to learn. I'm Norman Wahlberger. Thanks for listening.